Okay, next let's talk about the compact flash memory card. The L61 does allow you to use a compact memory card. You can use the 1784-CF64 card. This card offers a non-volatile memory flash to permanently store a user program and tag data on the controller. You can manually trigger the controller to save or to load from a non-volatile memory, or you can configure the controller to load from non-volatile memory on power up. The L55M controllers are fixed internal non-volatile memory, so you don't have this option to use this control flash card. The L566X controllers support a removable compact flash card for non-volatile memory. You can install the 1784 CF64 card in a socket or on the controller. The compact flash card stores the user program, the tag data, and the controller firmware. So this lets you upgrade firmware on the 1756L6X controllers without using Logix 5000 software or a control flash software. So what this enables you is to have your customer take a flash card and plug it into the controller, and they can load their new software. So if you have a change, this gives a client the ability to change it, or a maintenance guy that doesn't have the Logix 5000 experience and abilities, and he can actually change this. That's kind of nice. On the battery requirements, each controller ships with a battery. You get a BA1, a 1756 BA1. It's a lithium battery, and that bad boy doesn't last very long. So the L55M12 is 63 days. The L55M16 is 13 days. And this Series A L56L6X lasts 21 days. So if you put the BATM, the externally mounted battery assembly, this provides for longer battery life than the 1756 BA1. And so this battery will last up to 146 days on the 1756 L6X. This might have changed, I don't know, but the BA2, the 1756 BA2, and you can order this as a replacement, and it lasts for 8 months, so that's more like it. What this means to you guys is that when you install a battery and you lose power, your main power to the PLC rack, the CPU has to maintain its memory. And if it's relying on that little battery, it won't rely on it very long, and it will dump the program. So that when power comes back up a month later or something, I mean, that seems somewhat extreme in, around in modern, U.S. states and what have you, but certainly not overseas, and certainly not during shipping. You can actually ship one of these, and it gets out in the field, and it doesn't have a program, and they're wondering what's wrong. Okay, next we'll look at the 7-slot rack. What you would order is a 1756-A7. And again, what you want to worry about here is the spacing on this rack. So when you look at this PLC, you can see this is the actual power supply right here. In this example right here, we have a CPU, and then here we have some I/O cards. But you want to maintain 6 inches of ventilation on the top, 6 inches of ventilation on the bottom, 4 inches to the left side. And 6 inches on the bottom. Okay. What you want to do is on your chassis, you want to make sure you properly ground the chassis. This is really important. Can't overemphasize grounding. I'm just a stickler on this. You want to keep your ground wires as short as possible. You want to ground the 2 points. They give you 2 grounding points. And you want to run them to a single point ground, an earth ground. So you can see this earth ground is a common bus bar, and each rack in here is grounded. So that's real important that you ground that chassis. You'll get noise problems. You won't know what the heck's going on. It'll get goofy. Your analog signals will be bouncing around. also on your analog signals, if you don't properly ground the shields, they'll be bouncing around as well. Okay, the next card was a 1756 IB16 card. And just for those people that haven't actually played with one of these PLCs, you can see that the card actually slides in. There's a little opening, these rails right here. So you actually line it up very carefully and then slide it in the printed circuit card. So you want to align it at the top and then on the bottom, and then you want to press down on this tab up there, and there's another tab at the bottom here, and you want to press down on those, and it'll slide in, and you'll hear it firmly latch in, click in. Don't shove it in real hard. Look to see where it's at going, and then slide it in, and it'll click. Now, I didn't mention in here, but you can actually put keys on here, little tabs, and you can prevent people from sliding the wrong card in there and what have you. Slide the module into the chassis until the module locking tabs click, and you'll hear it. It'll go click. So you can actually see the locking tab. So when you want to pull the card back out, you actually physically have to push the top locking tab and the bottom locking tab simultaneously to pull the card out. And sometimes it can be a little difficult. And the wiring diagram for the 1756 IB16 is right here. You can see you've got 2 rows of terminals, and on the left, you can see that's terminal 2, and this side's terminal 1. So all the even terminals are on the left, all the odds are on the right. Terminal 2 N1 is this point right here. So if you were to wire this up, you'd see that if you follow this around down here, that's the positive portion of the battery, and the IB16, that's the IB, the B portion of it is a 24-volt input. So the negative comes around here and connects to the ground, and then that jumpers up to the ground 0, and then you're off and running. So now you can actually wire these cards up. And so when the push button closes, it allows 24 volts to be put on this terminal right here, N0, which causes that light, that N0, the 0 light to turn on, the LED to turn on, and the normally closed contact to close inside the PLC. And these are actually grouped, group 0 and group 1. Okay, the next card we wanted to talk about is the 1756 OW16i card. Now you remember in the SLIC 500 series, the RS Logix 500, you had a 1746 OW16 card. They don't have that one here. I haven't been able to find it. I did find the OW16i, which is the I again is the isolated. So these are isolated inputs. So here again is a front view of the OW16i module. And you have a jumper bar that comes with this, and you can actually kind of disregard the isolated portion of it if you want and just jumper all the commons together and not worry about it. The way this thing wires up, here you have for isolated wiring over here, you would have N0, there's terminal 2 here, and there's your out 0. So by putting power right here and then turning this output on, it would turn this coil on right here. For non-isolated use, you'd use a jumper, and you can cut it to length. Honestly, what I do is I take and put the entire jumper in there and cover every input, and then I only have to run one common or hot leg to this thing, and then it switches the outputs for each one. But if you wanted to isolate each one, you could do that as well. So you can see that these are just coils, and then here you have L2 here, L1 here, and it lights it up. And you can actually turn on coils and what have you. Okay, before we get into the analog cards, I really want to go over these shielded twisted pair wires. And Alan Bradley's done a pretty good job here of telling us exactly how to deal with them. And you need to make sure you do this. on your lab, on your desk or whatever, you might get away with this, but in the field, when you're running these wires clear across the plant, you won't get away with it, and you'll have noise issues, and you'll just kill yourself trying to figure out what's wrong with your unit. And all it is proper the drain. The shield on these cables, these twisted pairs, go over both wires, the insulated wires, and then you ground the shield, and then so if any stray voltage tries to jump onto that cable, it just simply goes to ground. So this is extremely important, so we'll go over this as well. So prepare one end of the cable for grounding. Remove a length of the jacket from the connecting wire, so you actually peel it back, and then you pull the foil shield and bare drain wire from the insulated wire. And I've rarely seen anybody do this right, but you should twist the foil shield to the drain wire, and then it's always a good idea to put some clear heat shrink over that twisted foil and drain wire, and then put a ground lug on it, okay, and then put some heat shrink on this end as well. Then you're ready to use this this wire. Ground the drain wire. Alan Bradley actually recommends grounding the drain wire at the field device as shown below. I actually have a hard time with that. I can't control the field device. I can only control the PLC, the panel itself, as we build them. So I always, connect it on the PLC side. And I probably know why they want to do it at the field side is because they don't provide any grounds for you. They're very limited on these cards. So what I usually do is I put a grounding terminal block underneath the PLC, and I usually lift it up so it's isolated from the back pan. And then if the client wants an isolated ground system, they can actually ground it. But then I take one ground and then run it to the main ground as well. And then here connect the insulated wire to the field device. And again, I would connect connect the ground on the twisted pair side on the PLC side, because I can't tell what they're going to do on the outside of this thing. And they might change out a device later too. Okay, and they tell you here, if you cannot ground at the field device, follow these steps. Prepare one end of the cable as in previous steps, and ground at an earth ground on the chassis as shown below. We recommend grounding the drain wire at the field side. If you cannot ground at the field side, ground at the earth ground on the chassis below. And connect the drain wire to the chassis mounting tab. Use any chassis mounting tab that is designated as a functional earth ground terminal. And there's the actual ground symbol. It appears next to the tab. And so here they recommend using a star washer, and there's their drain wire to the ground. But you can see, if you've got 16, 20 shielded cables coming into a PLC, this could get real messy, and you're not going to have enough points to ground 16 4 to 20 milliamp shielded cables coming in. So that's why you want to go ahead and order one of those bus bars, those ground pieces of bus bars that are made for this, and go ahead and ground them that way. And that way you have control of it, and just tell them not to ground it out in the field. If they ground it out in the field and you have a ground in the panel and a ground outside of the panel, then what you'll have created is a ground loop, which is probably worse than not having a grounded wire at all. Okay, so here, to connect the ungrounded end, prepare the non-grounded end of the cable, remove the length of the cable from the connecting cable, pull the foil shield and bare wire back, cut the foil shield and drain wire back to the cable casing, and apply heat shrink, exposing only the insulated wire. So this is the non-grounded end. In either case, only ground one end, and make sure it's a solid ground to a single point type grounding system. Next, let's look at the 1756 IF16 differential current wiring example. When you do a differential current wiring example, the IF16 16 input card can only have 8 analog inputs. And the reason I like doing wiring this card in a differential mode is because it allows me to isolate each 4 to 20 milliamp signal. That way I don't create another noise issue. So here's an example. We have channel 0 wired into N0 and N1, pin 2 and pin 4. And then you can see N1 here is jumper 2, I return 0. And here's a 2-wire example. You have a 4-wire or a 2-wire, and when you say 2-wire, that means you've got a power supply out here, and you're loop power supplying this. So here's your negative. The negative goes to this input right here. The positive goes to the positive of the 2-wire device, or yeah, that's right. And then the negative here goes to the positive here. And then you're actually, this could be like a resistor or a potentiometer or something, and it would act like a 4 to 20 milliamp input. And these are both current inputs. At 1756 OF4, this is a 4-channel current wiring example. And here a lot of people get burned on this one because they look at this and they want to connect the output to V out 0 and I out 0. And if it's current output, you want I out 0 here and return here. So if you want voltage out, then you would go from return to V out. And then obviously you would have to go into the configuration of the card itself and configure it for voltage or current output. Finally, we have the power supply. We said that it would be powered with 120 volts. The 1756 PA72 would do that. You want to install the power supply. The first thing you want to do is verify that the voltage jumper is present and is factory preset position. So you want to make sure you put this in the right position, this jumper. So if you have a 240 volt system and you plug 100, and you've got this set on 120, it's going to destroy the power supply. So if it's set at 240 and you've got 120, then it isn't going to operate well either. And the way you attach this to this power supply, or to the rack, this is the actual rack here. In this example, they've got a 4-slot rack. You align the circuit card of the power supply with the card guides on the left side of the chassis. And then you line it up and you slide it in, and it'll click in there as well. And then you've got 2 front screws here to screw it down. So here we slid it all the way in until it's flush with the chassis. Push it in. And then fasten the power supply to the actual chassis. There's two screws there. And then, as always, you want to connect that safety ground. So again, you're going to run out of ground points here, obviously. So you want to have probably a large ground bus bar somewhere in the panel so that you don't run out of ground wires. And then you can see here, they give you an example of exactly how to ground it. And they're real sticklers about it here. They've got the nut with a captive star washer. And it's really important. You really need to make sure you understand your grounds. And you need to make sure that you torque everything. You tighten the nut on the safety ground terminals to a torque of 12 inch-pounds. A lot of people don't realize this, but when you build a UL 508A control panel, you need to make sure that you torque all those terminals. And a lot of people don't. Rarely do I see torquing screwdrivers in servicemen's toolboxes and what have you. And you should go through there and periodically check them. Next, you want to go ahead and torque, connect your hot and neutral, so your line and your low or your neutral. And then you want to torque those terminals as well, in this case to 7 inch-pounds. and you want to use a number, the I guess the largest size wire you want to use is a number 14 AWG 75 degree C copper wire. And then here's a PB72B, and you've got your positive to the high side, the negative to the low side. So this is a DC input power supply, but we didn't ask you to select that. And you can see, oh yeah, you want to make sure, I've seen this before, they actually have a piece of sticker on top of this. And the reason the sticker is on top of these power supplies is as the wiremen are building these PLCs, they'll drop little pieces of wire and clippings and what have you inside the power supply. So Alan proudly puts a sticker on top of it. Well, the problem is if you don't pull the sticker off, then it's going to overheat. So you want to make sure you pull the sticker off. And you don't want to prematurely pull the sticker off and risk dropping some filings or what have you inside the power supply and damaging it during operation. So the label protects the power supply from metal shavings falling into the power supply and damaging it during operation. So make sure you remove it. Okay. Now here's actually a schematic of a diagram of the actual rack, and I guess some dimensions here. You can see the height of this is 6.22 inches, and the overall width of this 7-slot rack right here. So this is slot 0, 1, 2, 3, 4, 5, 6. So that's a 7-slot rack. Is 14.49 inches. So that's pretty wide, 15 inches wide and 6.22 inches tall. That's a fairly large power supply. Not to mention the tabs, it actually goes up a little higher than that. You can see 6.65 inches. So this is a fairly large power supply, or a PLC rack system when it's fully assembled. Okay, so next you want to design a PLC that uses the whole problem was to design this PLC with using these different cards, and we did that, and we picked all the cards out, and then we looked at the schematics of each card. Now we're going to configure the PLC in RS Logix 5000. So here I've got an example here. You've got the controller, and I named it homework number 19. And you can see you've got your chassis type right here is a 1756A7 7-slot chassis. And I put this CPU, this L61 CPU, in slot 0. You could obviously put it wherever you want in a control logic system. And then your chassis, your I/O configuration should look like this. So you've got your 1756 backplane, 1756A7. You've got your L61, and it gives you the name of the processor there. And then you've got slot 1 is your 1756 IB16. Slot 2 is your 1756 IB16. Slot 3 is your 1756 OW16I. And then 4 is 1756 IF16. And then 5 is 1756 OF4. So this is, at the end of the day, when you did this homework problem, this is what your initial program should have looked like as you configured your I/O backplane and everything. So what we've done so far is we've covered the PLC number 2 homework, and next we're going to go over the JK flip-flops and examples using RS Logix. Then we'll go over T flip-flops and examples using RS Logix, and we'll briefly touch on the Karnoff K-maps and examples using RS Logix as well. The JK flip-flops and examples using RS Logix 5000. The JK flip-flop is one of the most versatile of the basic flip-flops. Here I picked another type. It's a rising clocked JK flip-flop. So 0, 0, 1, 0, 0, 1, and 1, 1. When you have 0, 0, remember it doesn't matter what the clock does. There's no change on Q. A 1, 0, it follows J. See, Q follows J on the rising edge. And again, Q follows J on the rising edges here as well. if J and K are 1s, then it just it toggles Q. So here is an example of what this JK flip-flop would look like in a conventional gating system. So I've got this AND gate right here, and I called it AND gate 1, AND gate 2, AND gate 3, and AND gate 4. You can see we have a RS type or a NAND type latch, or it's an RS type latch right here. You can see how that works. And you've got your J input, your K input, and your clock input. So you've got your NOT Q comes back over here to this input, and your Q input comes back over here to this input. And these dots right here, these dark dots, are actually just connection points. These larger dots or circles are inversions. So these are NAND gates. So you have a NAND gate, a NOT AND, right? It's a NAND gate. So these are all 4 NAND gates. So what I did was I went ahead and created a Ladder Logix 5000 program of a JK flip-flop. First thing I did was created a clock. So when timer 2 is not done, this is closed, it starts timing out timer 1. So this is a 1 second on, 1 second off type clock. Whenever this is off, it unlatches the clock. Whenever this is on, it latches the clock, and it toggles back and forth. Now, we have our AND gate 1. Remember, these are NAND gates, and a NAND gate is just a NOT AND. So we had J, NAND 4, and clock ANDed together to create AND 1. Let's look at that. We have the clock, the J, and the NAND 4 output creates that AND gate right there. So that's what that is. J ANDed with NAND 4, ANDed with the clock is the AND 1A. And then we have not AND 1A is NAND 1, right? Because we invert it. Next we have the K ANDed with the NAND 3, ANDed with the clock equals the AND 2. Not AND 2 is NAND 2. So K, NAND 3, clock. Here it is. K, NAND 3, and clock gives you the output here. And then we have NAND 1 ANDed with NAND 4 equals AND 3. Not AND 3 is NAND 3. So NAND 1 ANDed with NAND 4. NAND 1 ANDed with NAND 4 is ANDed together, and that becomes an inverted NAND. That would be the NAND 3 output. And next we have NAND 2 ANDed with NAND 3 gives us AND 4, and then we invert that to get us NAND 4. So here we have NAND 2 ANDed with NAND 3 gives us the results of AND 4. Inverted is NAND 4. And then we take, let's see, I think we actually covered 7, 8, 9, right? So now we have 10. I just took the NAND 3 output and said that's Q. And I took the NAND 4 output and I said, well, it can't be not Q, so it's not Q. So it's, take this one and just not it. So we'll actually see this thing run. Hold on. Okay, so now we have the program running. And you can see this is normally closed, and this clock toggles on and off. It's a 1 second timer. It turns on for 1 second, off for 1 second. So you can see our clock pulse toggling. Now remember, on the truth table, if J and K are zeros, if this is 0 and this is 0, then there's no change. So it just sits there. And so you can see Q and not Q, they don't change. If J was a 1 and K was a 0, Q should be a 1, so we'll just go ahead and click that. We'll toggle it. And we'll see what happens. And Q was a 1 before, so it's, lo and behold, is still a 1. So if we go up here and we toggle J, and we toggle K, now Q turns off and not Q turns on. So this is how this works. Now obviously it doesn't check the positive rising edge, but it could if I put a 1 shot in there. Now what happens when both of them are on? When both of them turn on, then this Q and not Q should just toggle, right? So let's check that out. Which they do. Now, again, you know, you might say, why even do this? Well, what's the point of this whole thing? And the point of this is to tell you that you can take, you know, conventional gates and conventional logic, JK flip-flops, and convert them directly into ladder logic. This is a very powerful program, and it's extremely simple to understand, and that's the key here. So now this may or may not be the best way to do this. You know, like this NAND gate right here, NAND 4, it should technically, I guess, be toggling. I think I just saw it toggle, actually. Must toggle real quick. So you might come up with a different example. I don't know. So I don't know how useful an example like this would be. Okay, next we'll cover the T flip-flops in an example. We have a non-clock T flip-flop. The next state of Q plus will be a 1 if the present state of Q is a 1 and no T pulse occurs, or the present state is 0 and a T pulse occurs. So here you can see that whenever this turns 1, and basically all this thing does is toggle. It toggles on and off, right? So whenever the Q plus will be a positive, when the Q is a 1, the Q is a 1 here, and there's no T pulse. So if this is a 1 and there's no T pulse, this is a 1. And or the present state is 0 and a T pulse occurs. So if this is a 0 and a T pulse occurs, then you get a 1 out. And this is the way I understood this gate to look. You don't have a clock pulse. So here you have a toggle input. You have a AND gate. I did this with 2 AND gates and then a RS type latch with NAND gates here. And then I took the output of this one and tied it back to this one, and the output of this one right here and tied it back to this one. And then we have another type T latch. Now here you can see I don't have a clock, so I just called it T so you could see the action. And the same idea, right? If T is ANDed with NAND 4 is AND 1, and then T ANDed with NAND 3 is AND 2, and then, let's see here, 2, 3, 4, AND 1 is ANDed with NAND 4, gives you AND 3, not AND 3 is NAND 3, AND 2 ANDed with NAND 3 is AND 4, not AND 4 is NAND 4, and then NAND 3 gives you Q, and then I put the NAND 4 here, not Q, not Q. Okay, so here we're running a T flip-flop. This is in Ars Logix 5000. And so all I'm doing is toggling the T like a clock on and off every 1 second. And just like the T sounds, it's a toggle, and that's all this thing does is toggle on and off. So Q should just toggle on and off, which it does. And again, you know, what's the point of a T flip-flop? Well, it's really a memory location, and you know, that's how they used to store bits and memory locations, and it was a good way to do it. And as long as power was applied, it would remember it. But obviously, for PLC control logics, a T flip-flop or a JK flip-flop doesn't really have a place in this scheme of things. But certainly, you can understand and appreciate converting this NAND gates and AND gates into ladder logic, and it'll help you understand it. Okay, next item is Karnoff K-maps and examples using Logix 5000. We actually covered this in detail in Logix 500. I just want to touch on the subject and then prove the principles using Logix 5000. Remember the rules for reduction, right? You've got the pairs, the quads, and the octets. So you need to recognize these pairs, quads, and octets. And here we have that reduction that we saw earlier. And this is a pair, right? You see pairs here, we can see the reduction. We saw the two pairs. Quads, here you've got 4 ones in a row, and you can circle these. And when you circle these, this not C, not D, cancels out with this CD. And this C not D cancels out with this C not D. So you're left with AB, A ended with B. So this complicated Karnoff map, if you broke it into a complicated truth table and then you try to figure it all out and come up with a long expression, it can be simplified just to AB, A ended with B. And then here we have a group right here. You can see this is another quad. And so you can see that C and C don't cancel, but the D's do. The A's and the A's don't cancel, but the B's do. So you're left with A, C. A and it was C. So whenever you see 4 numbers together in a quad system like this, you can cancel out. You can make that a lot easier. You can also look at the 4 sides, the actual 4 sides, and you can actually look at that as well. So here in this example, you can see that it would reduce. So you have C, not D, not C, not D, so your not D stays, right? And then here you have not B, not B, not A, A, so your not B stays. So that would be your solution. Those two ANDed, or together rather. I was saying ANDed earlier, but it's actually or together. Octets, if you've got 8 of these in a row, you can look at this and you can see that all of these cancel and you're left with A. And here's an octet right here. The D and the not D cancel and all of these cancel and you're left with a C. Okay, now we're going to move on to the integrated practice programming instructions using the compute, math, move instructions. We have the add, the subtract, the multiply, the divide, the modula, and the negate. We also have the absolute value, the square root, and the compute. The add instruction adds source A to source B and places the results in destination. So here we have tank level 1 is added to tank level 2, and then the destination is total 1 and 2. And these are just tags that I made up. The sub instruction is a subtraction instruction. It's source A from source. It subtracts source A from source B and places the results in destination. So here we have tank level 1 subtracted from tank level 2, and the destination is tank 1 underscore minus underscore tank 2, and that's just a tag name, just so that you understand what the instruction was doing. We have a multiply instruction. The MUL instruction multiplies source A by source B and the places the destination in the results in the destination. The divide, the DIV instruction divides source A by source B and places the results in the destination. The MOD instruction divides source A by source B and places the remainder in the destination. The negate, the NEG instruction changes the sign of the source and places the results in the destination. The absolute value just takes the absolute value. So if you have a negative number and you want to know just the absolute value, it'll return an absolute value, a positive value. So even if it's a positive value in the source, it'll still return a positive value in the destination. If it's a negative value in the source, it'll return a positive value in the destination. The square root takes the absolute tank level 1 here in this example and takes the square root of it. So just the square root of 4 is 2, right? And that's what it'll give you. The compute is a nice instruction because you can take the destination or the actual expression, tank underscore level 1 plus tank underscore level 2, and then it'll take that expression or that algebraic expression there and put it in the destination. Compute results. Okay, so now what we're going to do is we're going to go ahead